To build a functional human organ from scratch, engineers have to replicate the architecture of life at the microscopic level. This 3D model illustrates the industry's fundamental biological bottleneck. Cells located more than 200 micrometers away from a direct nutrient supply rapidly undergo necrosis and die. This strict diffusion limit is the exact reason surgeons cannot currently pull a fully formed, lab-grown liver off a shelf. To construct viable tissue at scale, bioprinters must fabricate precise, perfusible vascular networks that step all the way down from 6mm surgical grafts to 10-micron capillaries. The path to full organ engineering is not constrained by a lack of biological understanding. It is constrained by the strict physics of spatial resolution and fluid dynamics. The dominant technology for handling living cells is extrusion bioprinting, largely because it can deposit material with extremely high cell densities. Reaching that capillary scale resolution introduces a mechanical conflict. Printing ultrafine structures requires pushing highly viscous bioinks through microscopic nozzle diameters. Forcing thick material through a microscopic tube generates immense friction. As the nozzle diameter shrinks, the wall shear stress during extrusion scales up exponentially. This scatter plot maps the physical consequence of that friction. As wall shear stress increases along the x-axis, cell viability drops off a cliff. The pressure deforms and destroys the cells before they ever leave the printer. Historically, laboratories relied on an expensive, time-consuming process of empirical trial and error, running batches of bioink through various nozzles just to see what survived the journey. This creates the bioprinting paradox. The exact hardware configurations required to maximize structural resolution inherently tear apart the living cellular ink they rely on. To solve this, researchers shifted to predictive fluid mechanics. By looking inside the extrusion nozzle, we map the exact forces at play. Standard hydrogel precursors extrude as non-Newtonian power law fluids, creating a smooth parabolic velocity curve as they flow. Modern granular or foam bioinks act differently. Modeled as Herschel-Bulkley yield stress fluids, their profile shifts to a solid plug flow, straight down the center, surrounded by intense shearing at the outer walls. Specific flow consistency and flow indices dictate these velocities. Cells caught in the central plug flow are protected, moving as a single unit. But cells trapped near the outer edges face severe friction. A bioink's underlying chemistry dictates its flow geometry, and that geometry predetermines the mechanical environment the cells will face. Fluid dynamics provides only half the equation. The other half requires calculating the specific viscoelasticity of the living cell. Mechanical resilience varies widely. Stem cells are highly sensitive to physical stress, whereas endothelial cells naturally withstand the heavy shear of in vivo blood flow. The critical strain model accounts for this variance. Damage occurs precisely when localized shear stress exceeds the specific mechanical limits of an individual cell type. We can map this shear stress profile directly onto the extrusion geometry. Stress is essentially zero at the dead center, scaling linearly to its maximum intensity out at the wall. When that outward stress surpasses a cell's critical strain radius, it enters the red zone. Cells flowing through this specific geographic boundary are forced to elongate and burst. If an engineer increases the overall flow rate or utilizes a higher viscosity bioink, the mathematics force this red death zone to expand inward, consuming more of the nozzle. Cell death during bioprinting is not random collateral damage. It is a geographically predictable failure zone, driven by calculable fluid mechanics. Instead of accepting this failure zone, engineers map it to avoid it entirely. This coordinate graph charts nozzle diameter against the flow rate. The bottom boundary maps the minimum parameters required for structural stability. The intersecting upper boundary maps the biology, charting the maximum stress allowed to maintain cell viability. The overlapping data creates a narrow target. This sliver is the exact printability window. By mathematically bridging bulk rheology with single-cell strain limits, engineers can guarantee both viability and resolution before a single drop of bioink is extruded. Even with a perfectly optimized printability window, extrusion hits a hard physical limit. It still struggles to safely manufacture the 10 to 30 micron capillaries required to fully bypass the 200 micrometer diffusion limit. To cross that final threshold, the industry is adopting hybrid, multi-scale printing modalities. This creates a strict division of labor. Extrusion is now reserved for macro architecture and larger vascular grafts, while light-based methods are deployed for the microscale. Systems utilizing digital light processing and two-photon polymerization use precise lasers to rapidly cure photopolymerizable bioinks. They sculpt dense capillary networks directly within a gel, without subjecting the cells to any shear stress at all. True organ-scale bioprinting is no longer constrained to a single modality. It relies heavily on the convergence of macro-extrusion and micro-photolithography. This predictive, multi-scale framework has triggered a significant influx of public and private capital, pushing these technologies out of theoretical modeling and into active global markets. Regulatory pathways are steadily clarifying. Authorities are actively studying and approving resorbable 3D bioprinted meshes and trauma care devices. While whole organ replacement remains the ultimate objective, immediate commercial returns are materializing in precision medicine, alternative drug testing, and food technology, where bioprinted scaffolds scale cultured meat production. The defining clinical milestone is occurring right now in reconstructive surgery: direct surgical anastomosis. Synthetic 3D printed biovessels are being sutured directly to natural host blood vessels, integrating them seamlessly with a living circulatory system. By mastering the mathematics of shear stress and solving the biology of the 200 micrometer limit, 3D bioprinting has graduated from an abstract physics problem into a clinically